For each functional group, we start with the naming, physical properties, etc. for that functional group. Then the next thing we do is we talk about how to make that functional group. So for alcohols, we need to talk about the reactions that you use to make an alcohol. And then we'll get into the reactions, what you do with alcohols, how you transform those into other functional groups, actually in chapter 11. But we start with reactions that you already know or allegedly already know. And so let's start with looking at how we hopefully know how to synthesize alcohols from from last semester. So how do you synthesize alcohols? And let's just sort of give you a big hint here and say using SN1 and SN2 reactions. So what reagents would I use for each of these two transformations? And if you think you remember, take a minute, stop the tape, and write in what reagents you would use. And if not, well, then I guess you'll have to just keep going with me. So let's start with the first reaction. So the first reaction, how do you convert a primary halide into a primary alcohol? Well, this has to be done using an SN2 reaction because primary alkyl halides only undergo SN2. And so what reagent would I use to substitute a bromine with an OH? And if you said to use hydroxide, you're right. So we would use a hydroxide. The hydroxide would come in and kick off the bromine, and so then you would end up with the primary alcohol. Okay. Can you use water for this reaction? So could we take a primary alkyl halide and react it with water to form the alcohol? No. Remember, primary alkyl halide plus weak nucleophile is no reaction. So you have no choice but to use hydroxide to convert a primary alkyl halide to a primary alcohol. Now, what would I use for a tertiary to convert a tertiary bromide to a tertiary alcohol? Well, this actually can only go by SN1 because it's a tertiary halide. And so I could use either hydroxide or water for that reaction. The water would be our solvolysis reaction, and hydroxide would be a strong nucleophile. Either one would work. So for primary alkyl halides, I have to use hydroxide. For tertiaries, I could use either. How about a secondary alkyl halide? What would I use there to convert that to a secondary alcohol? Well, I can, because a secondary can either undergo SN1 or SN2. I could either use, again, hydroxide or water. So I could do this by SN1, which would be with water, the weak nucleophile, and SN2 with the hydroxide. Okay, now that this is different, the tertiary is different than the secondary because in a tertiary case it's only SN1, whereas in secondary it could go by SN1 or SN2. How do we synthesize alcohols from alkenes? So what reactions would I use, or what reagents would I use to perform these two reactions? Again, if you think you remember, stop the tape, go ahead and write those reagents down and we'll see if you're right. So looking at the first one, it looks like I've added an H and an OH across the double bond, and this reaction has gone by what kind of addition? If you said Markovnikov, you're right. So Markovnikov addition, how do we add H and OH Markovnikov to a double bond? Well, we have a number of reagents, right? We could just simply use H plus H2O, or we could use the mercury acetate, water, and then are NABH4. So we could do mercuration, demercuration, or we could use H plus H2O to do Markovnikov addition of the H and OH. If we go to the next problem, how do I add H and OH anti-Markovnikov? So while this was Markovnikov, if I look at this one down here, this is anti-Markovnikov. So how do we add H and OH anti-Markovnikov? We would use BH3 and H2O2. And of course, when we do this anti-Markovnikov addition with hydroboration oxidation, remember the H and the OH add anti and cis. Up here, if you add H plus and water, you would get a mixture of cis and trans, 50-50. If you add the mercury, if you do mercuration, demercuration, remember you add the H and the OH trans, right? So that's how we can synthesize alcohols from alkenes. How do we make 1,2-diols, or what are called vicinal diols or glycols? Well, two ways to think about adding the two OHs to the double bond. We can either add them cis or we can add them trans. So again, if you think you remember these reagents, take a minute, write down what you think they are, and then we'll see if you're right. So how do I add two OHs cis to a double bond? That's called cis hydroxylation from last semester. I can use either osmium tetroxide and hydrogen peroxide, or we can use KMNO4 and base. All right, hydroxide, KMNO4 and hydroxide adds two OHs cis. Now, how do I add the two OHs trans? Well, the hint here at the bottom of the slide says we have to use two steps. There's no one direct method to make a trans dialcohol. And so we have to convert first the alkene into an epoxide, and then convert the epoxide, open that up to form the dialcohol. So how do I make an epoxide? Well, simplest way to make an epoxide is to react an alkene with a peroxyacid. And we open up an epoxide using H plus H2O. We use acid catalyzed ring opening. And since I bet that basically adds the OH to the molecule. Now, remember that you can also make epoxides in a two-step process. I could make the epoxide by reacting it with bromine and water first, and that would add the Br and OH Markovnikov, meaning that the bromine, the electrophile, would go to the carbon with the most hydrogens and the OH to the other. So I would end up actually adding an OH here and then adding the bromine there. And then if we added sodium hydroxide to this, the hydroxide ion will come in and deprotonate that alcohol. It'll form an alkoxide ion, which then is in perfect position to do backside displacement on the bromine to kick the bromine off to again form the epoxide. So you can either use peroxy acids, which would be my method, that'd be my preferred method with just one shot, or bromine and water, and then followed by sodium hydroxide. Okay. So we can make either cis or trans glycols or vicinal diols using either one of these reagents. The other method that we learned from last semester to make alcohols was one I'm going to build on here for the next few minutes, and that is that we saw with alkyne reactions that if we start with our alkyne, that we can deprotonate it with sodium amide, which is a strong base that will deprotonate, in this case, the hydrogen from the terminal position. This is a terminal alkyne, meaning that the triple bond is at the end of the chain. Of course, there's only a 2-carbon chain here. But that can deprotonate to form an alkynyl anion. The alkynyl anion is a strong nucleophile as well as a strong base. But if we use this as a nucleophile, we can actually add this to carbonyl molecules. And we're going to get into this reaction a lot more here over the course of the remaining part of the lecture. But when you have a carbonyl, remember a carbonyl carbon-oxygen bond has a delta plus and a delta minus on the oxygen. The oxygen actually has 2 lone pairs and will easily bond to hydrogen, so the oxygen is a nucleophile. But the carbon, because of its delta plus charge, because this oxygen sucked a little electron density away from it, makes this carbon electrophilic. And so what can happen is that your alkynyl anion can come in and attack the carbonyl carbon, and if it stopped, you'd end up with a carbon with 5 bonds, which isn't allowed. So as the nucleophile comes in and attacks this carbon, the carbon-oxygen bond, one of those breaks, and that pair of electrons goes to that oxygen. And so what we end up doing is we end up forming a carbon-carbon bond, and then our oxygen has 3 lone pairs on it, which makes it then an alkoxide ion. And so this was what we called last semester, what we call from chapter 9, this is called an acylation reaction, because I'm adding basically what's called an acyl group to the nucleophile. So carbanion comes in, forms a carbon-carbon bond, and then we form this alkoxide. Now, we have to do this as basically a first step, because we have to leave this as an alkoxide, because in the second step then, we're going to go ahead and we're going to add acid to that to protonate the alkoxide to make the alcohol. Let's write this down to be formal. Now, if we had acid or water present, this alkynyl anion is a strong enough base that it would react, and so we would deprotonate it, but then we would reprotonate it with the acid. So we have to basically make the alkoxide in one step and then add the H plus H2O in a second step to form this alkynyl alcohol. Okay, and so this was the other reaction that we learned last semester on how to make alcohols, and this is by taking a carbon nucleophile and reacting it with a carbonyl. Now, what we're going to talk about for the remainder here is this is a great reaction because it forms a carbon-carbon single bond. And in organic chemistry, whenever you form a carbon-carbon single bond, that's an important reaction. If you go back through the early 1900s to, let's say, the mid-1900s, you would have found that people who came up with ways to form carbon-carbon bonds, they all have Nobel Prizes, and the names are all named after them. And so forming carbon-carbon bonds is a premium in organic. And this is just one example. This doesn't have a person's name associated with it, but we will talk about a reaction that does here in a minute. Now, does this mean that if I have a carbon anion, that it'll always react with a carbonyl at the carbon-oxygen double bond so that I form a CC bond, form an alkoxide, and then add H plus to it? And the answer is yes. So what I really would like to do is to not just limit this reaction to be alkynes. I'd like to be able to do this reaction with, I don't know, with a methyl group, or maybe an ethyl group, or some other carbon group. Now, we'll talk about how to make that again in a moment. But the advantage here of the alkynes is that we can easily deprotonate terminal alkynes with amide base and form the alkynyl anion. How do we make a CH3 minus? How do we make a CH3CH2 minus? Because there are no bases that are strong enough to deprotonate carbon-hydrogen bonds. You might say, but you did it down here. Yeah, I know, but the triple bond creates a more acidic hydrogen than normal. So if we can form these carbon anions, which I'm going to call carbanions here in about 10 seconds, then I can do the same reaction. I can add the carbanion to a carbonyl, form a carbon-carbon bond, and basically make an alcohol. And so these are the new reactions that we're going to use to make alcohols. So let's talk about carbanions and compare and contrast them with carbocations. So here's a carbocation, or here's the precursor to a carbocation. If you have a halogen attached to a carbon, the carbon-halogen bond creates a delta minus charge on the halogen and a delta plus charge on the carbon. Of course, if this carbon-halogen bond breaks, we end up with a carbocation and our halide ion. The carbon then becomes an electrophile, and we can react with a whole bunch of nucleophiles. What I'd like to do is I'd like to switch the reactivity of carbon from being an electrophile to now being a nucleophile. And so what I really need is I need a C minus. That means really a carbon with a lone pair. And then, of course, if you have a C minus, you need a counter ion to go with that. We just can't, if I said go get some chloride ions, you couldn't go down to the stockroom and just pick up a bottle called chloride. You'd have to have either sodium chloride or potassium chloride or calcium chloride. So we'll need a counter ion for our C minus. And so the counter ions that are used for this are most commonly alkali metals and one alkaline earth metal. So things like lithium, sodium, and potassium are the alkali metals that could be counter ions, and magnesium is an alkaline earth metal, and that's also can serve as a counter ion to that C minus. So the question is, how do you make these carbanions? Okay, now these cations, actually we're going to treat them as if they don't play any role. We're going to just treat this molecule as if it was a C minus with nothing else attached to it. Now that's not, this counter ion does play a huge role, and whether it's lithium, sodium, potassium, or magnesium does sometimes affect its reactivity, but that's more detail than what we want to get into in this class. I actually did my PhD research and postdocs and continue to do research using alkali metals and carbanions or alkoxides, and the counter ion can make a huge role, or a huge difference, but I won't go down that road at this point. So how do we prepare these carbanions? Well, first, these carbanions are called organometallic reagents because they've got an organic portion and a metal. So here's what we do. We take our halogen, we take our alkyl halide, and we add to it the metal. Now, if it's lithium or sodium or potassium, and most often it's lithium, what we end up doing is we end up adding 2 lithium metal atoms to the alkyl halide. Okay, so actually I'm going to have 2 lithiums here. I can also do this reaction if I add 1 magnesium metal atom to the alkyl halide. And so here's what happens. I'm going to go ahead and I'm going to erase this 2. So for alkali metals like lithium, what we have is we actually have, here's the Lewis dot structure of those 2 lithium atoms. And of course, the carbon halogen bond is made up of 2 electrons. And so what happens in this reaction is this is what's called a single electron transfer reaction. And what that means is what happens is I'm going to split this carbon halogen bond in half. I'm going to pair up the lithium with the carbon, and I'm going to pair up the second lithium with the halogen. So I'm going to end up forming the carbon lithium bond, although I'll come back to that in a moment, and lithium and the halogen. And what happens is that because the halogen and the carbon atom are both more electronegative than lithium, the carbon is actually going to get both electrons and the halogen is going to get both electrons in this splitting of that bond. And so I'm going to end up with a carbon with 1, 2, 3, 4, 5 electrons, so it's going to have a negative charge, and the lithium with a +1 charge, and then over here another lithium with a +1 charge, and the halogen with the minus charge. So by this single electron transfer reaction, we end up forming our carbanion with a lithium counterion, and we also then form lithium halogen, or a lithium halide. So if this was a bromide, we'd form a carbanion and lithium bromide. This reaction can be done with lithium, sodium, or potassium. It's most often done by lithium, and it could be done with any halogen. It turns out that iodine is the more reactive of the halogens that you could use. It's easier to form carbanions from iodine, although it has some side reactions. We most often use actually bromide as the halide to make an organolithium compound. And that's what this would be called. This is either called a carbanion or an organolithium reagent. Reaction is very similar with magnesium. So if you take magnesium, now that's an alkaline earth metal, so it has 2 unpaired electrons. When you react that with the halogen, you can now think of it occurring this way, that I'm going to end up donating one of these halogens to the or one of these electrons to the carbon, one of the electrons to the halogen, and so I'm going to end up having my carbon with its lone pair, and then I'm going to have the magnesium with nothing because it gave up its 2 electrons to the halogen and the carbon, and so then I'm going to end up with the halogen now having its pair. So 1 electron went to carbon, 1 electron went to the halogen. That means this carbon has a -1 charge, the halogen has a -1 charge, and of course the magnesium now has a 2+ charge. And so that we oftentimes write it as if the carbon was bonded to the magnesium, which is then bonded to the halogen. And I suppose that's probably true, but we're going to treat the molecule as if it looked like this. I'm going to call this magnesium bromide counterion as having a +1 charge, because that's in essence what it has, with a +2 charge on magnesium and a -1 charge on the halogen. So these two kind of look the same. You've got a negatively charged carbon with a one positive charged cation or counterion. Now when magnesium is involved, this is called the Grignard reagent. When you have lithium, lithium is called an organolithium reagent. And so a lot of my thesis and postdoc work was done with organolithium compounds, and I can tell you more than you would ever want to know about those, but I won't. So we can use either one, and we're going to use either of these interchangeably. So this is how you make carbanions. React an alkyl halide with metal, either 2 equivalents of lithium or 1 equivalent of magnesium. The person that developed magnesium reagents was Victor Grignard, and so the reaction name bears his name. And Grignard won the Nobel Prize for this reaction because it's a great way to form carbon-carbon single bonds. Now, when you form these organometallics, and in this case it doesn't matter whether it has a lithium as its counterion or whether it has a magnesium bromide as its counterion. The C- can either act as a nucleophile or it can act as a base. And that's something that we have to be careful of, because if we wanted our nucleophile to react with an electrophile, then I'm going to end up forming my carbon-carbon bond. But I have to be careful that when I do this reaction or when I make this reagent, that there's no compound in there that has an acidic hydrogen, because the C- will act as a base and it'll deprotonate the acidic hydrogen, and then what I end up doing is just simply protonating the carbanion, and then it's no longer a nucleophile, so nothing will occur. So we have to be careful that when we make organolithium compounds or Grignard reagents, we have to keep molecules with acidic hydrogens away from it. These molecules are water. If you have an NH, that would be deprotonated, or a carboxylic acid will also be deprotonated. And although remember the whole point of this is to make alcohols, we also have to keep alcohols away from these carbanions because they will deprotonate them and it'll just form a side product that we can't use. So if you do this in lab, you'll have to make sure you dry the glassware out, keep all the moisture out of the reaction, etc. And so we have to be careful when we do that. Okay, so there are a lot of advantages of using organometallics, and organometallics are just simply the only way that I can convert a carbon into a C- for most carbon hydrogen, or for most carbon molecules. Okay, a carbon-carbon triple bond we could deprotonate, but if I had a halogen attached to a benzene ring, all I'd have to do is react it with lithium metal, and I'd end up making the lithium carbanion here, and then of course as another product I'd have lithium bromide. If I tried to deprotonate a benzene ring to form a minus, and I might use a C- species, so this N-butyl lithium turns out to be this commonly used reagent, this isn't strong enough to actually deprotonate a carbon-hydrogen bond. So this is really the only way that we can make C-. But the great thing about this is I know a lot of reactions to make alkyl halides, and so wherever I put the bromine, that's where the C- species is going to occur. So we'll see that as we go through all the different Grignard reactions or organolithium reagents. So if I go back here to what we learned last semester, we learned that if I did have an alkyne, I could easily deprotonate it with amide, form this carbanion. Now I'm calling it a carbanion. Last semester I called it alkynyl anion. But now that nucleophile will attack a carbonyl, I can form my carbon-carbon bond and form my alcohol. So now what I just did was I just showed you how we can make different carbon nucleophiles, how we can form carbanions. And so if I can form a carbanion, it's going to easily attack the carbon of the carbonyl. It's going to form a nucleophile carbon bond, And of course, in forming the nucleophile carbon bond, I've got to break the CO double bond and give that pair of electrons to the oxygen. And again, if I put in the 3 lone pairs, there they are for the minus charge. So again, this is my first step in the reaction. And then the second step is just simply to add H plus to it, protonate the alkoxide to form the alcohol. So now I've formed a carbon nucleophile bond, and in particular, if I started over here with something like CH3 minus, let's say MgBr plus, I would end up forming the CH3 carbon bond, and I'd end up forming my final product having a CH3 to carbon bond as well. So all I got to do is be able to make my Grignard. How did I make my Grignard? Well, I simply took the alkyl halide and reacted it with magnesium metal to get the Grignard. Now I can make a whole variety of nucleophiles, add them to carbonyls, and make alcohols. In the next lecture, for the next period, what we're going to do is we'll actually use some other negatively charged nucleophiles. And then about the middle to late part of the semester, we'll talk about using a little weaker negatively charged nucleophiles. But this mechanism of adding the nucleophile to the carbonyl occurs over and over and over again for the next couple of lectures. Okay, so if we make a C minus, I can add it to a carbonyl. Now I'm not limited just to carbon-carbon triple bonds. I can use alkyl groups to make carbanions. So I'm going to use R minus as my generic carbanion, and I'm going to use my M plus as my generic metal. So this could be, for instance, a CH3 minus Li plus, or it could be a CH3 minus MgBr plus. And remember, the MgBr is plus because the magnesium 2 plus and the Br is minus 1. So that's a net +1 charge. So if I react a ketone, and remember a ketone has 2 alkyl groups attached to a carbonyl, and I reacted that with a Grignard, I would end up with a molecule that now has 3 alkyl groups attached, and when I protonate that, I form a tertiary alcohol. So if you want to make a tertiary alcohol, use a Grignard and a ketone. That'll get you a tertiary alcohol. 2 of the alkyl groups in that alcohol came from the ketone, and the other alkyl group came from the Grignard. So we can make a variety of different tertiary alcohols depending on what Grignard and what ketone we use. You want to make a secondary alcohol. How would you do that? Well, secondary alcohol has 2 alkyl groups on it. So we come back and we say, well, if I react my Grignard with an aldehyde, that then gives me 1 alkyl group. And so this carbanion comes in, attacks that carbon, moves the pair of electrons up onto the oxygen. We make this alkoxide ion, and then in a second step we add H plus to it. We should probably write arrows here showing the protonation step. We protonate the O minus to form a secondary alcohol. So if you want to make a secondary alcohol, react an aldehyde and a Grignard. How about if you want to make a primary alcohol that just has 1 alkyl group? That's easy enough. You just say, well, I need an aldehyde that has 2 hydrogens. And so that aldehyde is called formaldehyde. That's the name of the 1-carbon aldehyde. So react that with a Grignard. Your C minus comes in, attacks that carbon. We end up now adding the alkyl group to our formaldehyde. We end up with a CH2 group with an O minus. In the second step, go ahead and add the H plus to the O minus, and we end up with a primary alcohol. So you want to make a primary alcohol, react formaldehyde and the Grignard together. Okay, and we'll do a couple problems here to end this. Now, are these the only functional group or only ketone or only carbonyl groups that you can add to a Grignard? Formaldehyde, a normal aldehyde, or a ketone? Well, no. And we'll talk, the last one we'll talk about is adding CO2 to a Grignard. But then in the next period, we will go ahead and I'll show you a couple more carbonyls that we can add that we can get other functional group. We can make other functional groups. So what happens if I add CO2 to a Grignard? Well, CO2, there's a slight modification. The carbon's slightly positive, and then each of these oxygens are slightly negative. And so what happens is your carbanion comes in and attacks this carbon, and then you break one of the two CO double bonds and give that pair of electrons to that oxygen. And so what I end up doing, let me rewrite this molecule so that if you're trying to keep track of it, what happens is your R group ends up there, and then your O minus species ends up to the carbon on the right-hand side. So if you're keeping all the atoms the same, this is the product that you would get. Well, looking at this, what is this? This is actually a deprotonated carboxylic acid, right? Because we got C double bond O and then an O minus. That's a deprotonated carboxylic acid. So when you react carbon dioxide and a Grignard, you'll end up forming a carboxylate or a deprotonated carboxylic acid. In your second step, if you just add H plus to it, you go ahead and you make the carboxylic acid. So you can make a variety of functional groups from carbonyls and Grignards once you know how to make the Grignard or the organolithium reagent. Okay. So let's do a couple real problems here, and then you can do more, and we'll do more in class. You do more for the Blackboard quiz. But let's say I was to react CH3, CH2 minus MgBr plus with this molecule, which I'll call methyl ethyl ketone. So if I was to react these two, what product would I get? Well, first, if I give you this reaction, here is the way I'm going to write it. I'm going to say you react these two together, and then over the arrow I'm going to say then H plus H2, then H plus, either just then H plus or then H plus H2O. So this indicates the two-step reaction. I'm going to react Grignard and carbonyl, and after that reaction's over, then I'm going to add my acid. So what happens in this case? Your carbanion comes in, attacks that carbon. We end up now forming this alkoxide. Come down here. I'm going to change pen colors here for a moment. So if I reacted this CH3, CH2 minus, here was the original group that came from the Grignard, now attached to that carbon. So I formed that carbon-carbon bond. I've now formed a tertiary alcohol or tertiary alkoxide. And now I would go ahead and add my H plus, which is just simply going to protonate the O minus so that the final product will be this tertiary alcohol. Okay. What if I wanted to add an isopropyl group to, let's say, this aldehyde. Again, there'd be a MgBr counterion. I would then say, okay, I'm going to use my then H plus H2O step. So what happens here? Carbanion comes in, attacks this carbon, pair of electrons moves up there, so that I form this alkoxide. Now, for those of you that are saying, where does the magnesium mysteriously disappear to? Well, it turns out that this O minus needs a counterion, which would be the MgBr plus. And then when I add the H plus in the second step, it actually the H plus would be like HCl or HBr, and so then the magnesium just becomes MgBr2 or MgCl2 or MgClBr. So when I add my proton in the second step here, I'm now going to go ahead and then form the final product. So in this molecule, in the molecule that I just made, the hydrogen and the ethyl group came from the original aldehyde. And then this isopropyl group is what was added from the Grignard. Okay. And in class, what we'll do is we'll start thinking about, if I gave you this alcohol and said, how would you make it? You could basically choose any of the alkyl groups as the Grignard, and then the other two groups would become what was in the carbonyl to begin with. But we'll talk about that more in class. At this point, what I'd like you to do is just to be able to think forwards. All right, last sample reaction then. And this one I've actually done in the lab, because what we've sometimes I want to make at one point I wanted to make a carboxylic acid directly from carbon dioxide. And I won't get into the reasons for that, but I did. And so what I ended up doing was making this organolithium compound. Now remember, the counterion, whether it's lithium plus or MgBr plus, is pretty much the same. It's the C minus that's important. How did I make that? Well, I just simply took my alkyl halide and reacted it with 2 equivalents of lithium. And so, of course, then up here I would have had a lithium bromide as an extra product. So my CO2 has an oxygen double bonded to a carbon, 2 oxygens. So the C minus comes in and attacks this carbon. Pair of electrons moves over here. And so I end up with the oxygen bonded to the carbon. I end up with an O minus over here. And then I ended up with my CH2, CH2, CH3. So the propyl group came from the organolithium or the Grignard. And so then in the final step, I added my H plus. And so the carboxylate, the deprotonated carboxylic acid, added the proton. And so what I ended up forming, if I rearrange this, is simply CH3, CH2, CH2, and then the carboxylic acid part. Okay, so it turns out that Grignard, and one of the reasons why I won the Nobel Prize was because this reaction forms carbon-carbon single bonds. And it gives you a whole variety of reactions that you can do where all you have to do is be able to make that Grignard reagent and then go ahead and react that with a variety of compounds, from aldehydes to ketones to formaldehyde to carbon dioxide. And you can make primary, secondary, and tertiary alcohols, as well as then making carboxylic acids. So that's the versatility of the Grignard that is the important part. Okay, so what have we seen? Well, got to know our reactions from last semester. We have to know how to make alcohols. We have to know, remember our SN1 and SN2 reactions to react either hydroxide or water, depending on whether it's a primary, secondary, or tertiary alcohol or alkyl halide. That will let us make primary, secondary, or tertiary alcohols of our choice. Alkenes, we can convert to alcohols by either adding H plus H2O, mercuration, demercuration, if we want to do Markovnikov HOH addition, or hydroboration oxidation if we want to add anti-Markovnikov and make the anti-Markovnikov alcohol from the alkene. We have to remember how to make diols. If we're going to learn to synthesize alcohols, this is what we know. Diols are made either by cis hydroxylation with osmium tetroxide and peroxide, or the KMNO4 base. If you want to make the trans dialcohol, you need to convert the alkene into an epoxide and then open it up with H plus H2O. You can also make alcohols using alkynyl anions. Deprotonate them, react them with carbonyls, like ketones in this case. You can do the same thing with aldehydes. React those, and then you will go ahead and make the alkoxide ion and then add H plus to it. We learned this reaction last semester. We now expanded on it and said if you want to make an organometallic reagent or a Grignard, both of which are carbanions, react the alkyl halide with either two equivalents of lithium metal or a magnesium ion or a magnesium metal, and that will give you the carbanion. And then we can react the carbanion with all sorts of carbonyls and do in essence what we did with the alkynyl anions in terms of forming a variety of different alcohols. Okay, so our review, what reactions do we know how to make alcohols with, and now how beginning some new reactions, all from carbanions, all from organometallic reagents, these Grignard reactions. Okay? So go ahead, I would give the book maybe a perusal, and then you can go ahead and do the pre-class Blackboard quiz. And then if you had any questions along the way, bring them to class and we will talk about them. We'll start with questions and then we'll do some more of these reactions and some more of these syntheses.